inventor
installed it.
Yeah?
Yeah.
Installed it?
Yeah.
Were you able to download a subsystem from a cubesat manufacturer, import it?
You mean modeling us?
Yeah.
No. Because in one more system we are still installing it.
Yeah. Don't worry, we'll take care of it. So the one of the troubles always is the formats, right? You on the website, say cubesatshop.com, you find the STP step file. Can you import it into your CAD software of your choice? Then can you manipulate it and so on? That's something I recommend you to figure out quickly. Is it working?
Here
It's my fault. I'm too late today.
yeah, here it's showing something.
Plug it in.
No, it doesn't change once
Sit down, please.
Oh, you want?
So yeah, for system engineers that would be important. The payload paper. How was the reading?
I did not finish or start even the paper because I had too much to do. But I nearly finished all the chapters we were supposed to read in the smartphone.
Okay, let's say it again. Did you read the paper?
Yeah.
Not at all?
Not at all.
Did you check the table of contents?
Not at all.
Then then you will have to do that.
I know.
Yeah?
And it was not clear to me if we need to do all the homework for today or for next lecture.
Yeah. Okay.
Yeah, same.
Okay, good. We'll talk about this.
Also, I cannot see the table of contents.
And the others, I had uploaded this PDF file of the smart space engineering, say, reference book. Did you have a look into it? Yeah. I recommended to read the path on Keplerian elements. Was that something new to you? Was it boring?
it was not exactly new.
Okay.
Not new, but more detailed.
Yeah. Was it clear? Was it clear, the part on the Keplerian elements? Okay.
Well, to be honest, I'm looking, but not like with
Yeah.
a lot of attention because it was. I didn't expect that we need to read everything until today.
Yeah. So the thing is,
I didn't understand that part.
yeah. Okay. Well, I had actually hoped you read it today. Being Keplerian elements something that you learned in the other courses, or was, say, at least addressed in the other courses. So if it was something new, then it's important. If it's not new, then it should be a quick read. Well, we'll to some extent we'll look into Keplerian elements today too. It is important for payload team to understand at least the basics of it. There will be a presentation on it next week with some more details. You don't need to know all the details. You don't need to understand how the GPS signal works, which is explained in the paper. I don't understand that. What is important for you is, in order to design a mission, is what is the mass of the subsystem. How much power does it need? What other needs does it have in terms of altitude control? I discussed it last week. If you have a high precision camera, you need to know very well where to point your camera. If you have other payloads, you may not need that. So you need to understand what are the overall needs. To some extent, you can see it as a black box, a smaller black box. For the others, a big black box. For you, it's a smaller one. Yeah, this is that you can tell these guys, I need this kind of altitude control. It's 90 degrees, so satellite is okay if it does like this, or you need 1 degree or 0 to 1 degree, so 1 minute accuracy. So this guy, you need to tell these guys.
So the payload consists out of the sensors and the communication system.
So the payload in any kind of spacecraft is the thing that gives the mission a purpose. It can consist most likely out of some hardware. Since we want to use GPS reflectometry, it will most importantly consist of a GPS antenna, otherwise you don't receive the signal. And then most likely some kind of, say, electronics computer that processes that data to some extent until it is a useful information.
So the TTNC is not my part.
So the telecommand is there, it's like a communication. You give the mission a purpose.
Because some teachers were talking about communication
Payload. So this is, yeah.
Quite ambiguous what is now.
Quite right. This ambiguity, that's something you, first of all, you all, Natalia, Michael, so you all need to work around a bit, because there are very different nomenclatures for missions. It's actually mentioned in the SMAT that I gave you. The Department of Defense in the US, NASA, ESA, they have very different names for the same thing. It's traditional, and you need to figure it out. So why are we here within this course very often talking about communication payload? Is because these guys, Simeos and so, they have an attitude of geostationary TV satellites, and it comes because there's a close relationship between SNT and SES. SNT being Institute here, and SES. And SES does geostationary satellites for communication. Right? They receive the TV signal and send it back. So the payload is doing communication. So the purpose of the mission is some kind of communication. But in the mission that we do here, the purpose is to receive some GPS signals and determine the moisture content of the surface.
But also communicating it back to Earth.
Without communication, there's no mission.
Yeah.
There's no point. If you do not receive the information, we don't do anything useful.
So will I also need to look up for an antenna system that is providing us data, or can I rely on the TTNC antenna?
So the TTNC will be what frequency, most likely? How will we communicate to our cubesat?
The problem is that we don't know at the moment the altitude of the cubesat.
Will be low Earth orbit, so between 400. So as a matter of fact, you know the altitude is a defined constraint. I gave it to you.
Yes, but exactly that means that different altitude is generate different size of the windows of the transmission for the satellite.
Yes. So I gave you the constraint. The altitude will be between 400 and 600 or 650. Yes. So it's quite a constraint. Which are the typical frequency used for CubeSats? So I give you the answer. It's VHF and UHF. Very typical. That's what we will use. If you went to cubesatshop.com and you look into the TTNC antennas, you will see it's mostly VHF, UHF. Sometimes you have S-band, X-band, but it's in CubeSat world not common. Now, these antennas are made for VHF and UHF. Is your GPS signal in that frequency range? Check, it's not, it's L-band, which means the antenna that they will use to communicate your data down, you cannot use them to receive. You will have to have your own antenna. GPS antenna. As it is on the phone, there's somewhere a GPS antenna involved. How exactly that works, actually, I don't know. you'll find it. You Google it, cubesat GPS antenna, you find it. If you don't, come to me, send me an email. I'll give you, for example, some specs for a GPS antenna of the one that we are using, that we are buying for our prototype that we will use in the third semester to experiment it. You will experiment it. I can send you the specs of it. So try to get a good overview of the system engineering aspects, or the global engineering aspects of your payload, which consists of some kind of device to process the data to some extent, to receive the data, and then you will have to send it to those guys. They send it down to Earth. Don't send it down. And for the geostationary satellites, the purpose is the communication itself. So that's why they often speak about a communication payload, which is confusing sometimes. If you have a human mission, the purpose is to bring an astronaut to the moon. So your payload is the human. Yeah. Try to. So this is the reading that I gave you last time. It's very basic things. It should either be an easy read because you have seen it before, or it's important. If you have questions, please come to me. Yeah. Good. We'll go a little further today, and we look into the astrodynamics in low Earth orbit. Before we go to the details. In the European Space Agency, like they do in NASA, like they do in car manufacturers, they do these kind of CDF studies, concurrent design. That's what we do here. We have groups, every person takes care of a particular aspect, and there will be in the end a report, what I mentioned. End of next semester, you will all write together one report like this one. Here I participated for the European Space Agency. We studied how to send a probe to Mars to collect some atmospheric gas from it. What I would recommend you is to browse through just to get a feel of it, and then get further over the course of the hour, just to get a feel what you expected to do.
Is the final report, you expect length, this range? This?
Well, it doesn't need to be that extensive, I would say.
How many words or pages?
I can't say by now. The goal, I mentioned it last time, is that you need to prove here that this mission, with the constraints and requirements that I gave you, is feasible. So there needs to be a design saying, this is how we put together a satellite and the mission in order to measure what I asked you to measure.
And you know it's feasible, right?
If I knew, I would not ask you to say, no, I don't.
So what if there is the possibility that the project won't succeed?
Say it cannot fail if you do it right. So what could be a problem? For example, that the measurement method produces so much data that it's not possible to downlink it with UHF. There could be a blocking point that you discover. At the moment, I don't know how much data payload people, so you need to figure it out. You have seen the requirement that I gave you is 20 kilometers times 20 kilometers resolution, once per week landmass. You could produce possibly so much data that you cannot downlink it with UHF. Could be. I don't know that. Then you will have to propose you use a different communication system. Or you will propose that certain data is processed on board, so that only a reduced amount of data is downlinked, so that they can do it. But then you need a more performant computer. That is, you have to define the requirements, have to exchange it, so that in the end we'll figure out if that's true. And that's what we did here, for example, the space agency. And you have a artistic background?
Yes.
So for space missions, they always do some kind of patches. Okay.
That's beautiful.
I want you to think of it, not to do it yet.
Okay, for us? Or
For this mission.
For this mission?
Not now, not next week, But by the end of this semester, we should find a good name for the mission,
Yes.
and maybe we want to have a design for a patch.
Okay.
And so, and this space math program is about interdisciplinarity. So you have an artistic background, bring it in. Bring it. I cannot give it to you. It's very important to me. It's a mission I was working with.
Okay.
Yeah. It's usually circular and has. It says
some-
what the mission name, and it can be open. Yeah. Okay. Good. Let's talk about LEO, low Earth orbit astrodynamics. There's some literature. This map I mentioned is I gave you the old one as PDF because I don't have the new yet as PDF, and it should have been in the library, but it's not. The old SMAP that I gave you is just fine for your purposes here. That's something you should have seen before. Our friends, the Keplerian elements. How many are there?
6.
Good. What do they? Oh, no, I forgot what I wanted to bring. The most important. Can I borrow a pen? Or the pen. What do the Keplerian elements say? Roughly, a few words.
The position.
You want to define each of them or in general?
If in one sentence you have to say what the Keplerian elements do,
They describe the orbit of a satellite.
yeah? Everyone agrees?
Yes.
So there are, let's say, 3 that define where the position of the ellipse. I'll draw it this way. And draw an ellipse around the Earth. Right, so this the ellipse around the Earth. And so the ellipse could be, if this is the ecliptic plane, so say you are the sun on the Earth, okay? So you can have the ellipse rotating like this. Who knows which parameter this is? It's the right ascension of ascending node. So, for example, if now it's spring, you are the sun. No, I think it's like this, and then we have now the plane is 0, has a 0 angle with you. Now, if I move to summer, then I should be somewhere outside there. I will make it easier. Let's let the camera be the sun, okay? Okay. We'll move from here to here. Then this angle changes,
Yes.
right? Right ascension of ascending node. The inclination is this movement of the eclipse,
Yes.
right? And then, who knows what this point is? Say it again. Perigee and apogee. So this ellipse can be like this or can be like this. An argument of perigee. So these are 3 tell you where the ellipse is. And then you still need to know where your satellite is. Sorry.
Shape.
First of all, the shape of the So it could be very elliptic, so this is quite elliptic, but it could be of an extreme ellipse, and it could be a circle. So that's eccentricity. Right? And then there's the semi-major axis, which is in essence what?
Or
In essence,
half of them.
yes. Quite right. So if the eccentricity is 0, you have a circle, then the semi-major axis is the altitude, or sorry, the radius.
The radius.
The radius. So it's the shape, and then the last point is where on that ellipse is the true anomaly or mean anomaly, or there's different ways of putting it. And the point being, 6 parameters tell you where your satellite is around the Earth, or the Earth around the Sun, or whatever object around a bigger one.
Can I ask a side question?
Yes.
Is it possible to have perfectly circular orbits like astronomers in the past believed they were?
perfect. So in reality, nothing is perfect.
Yeah.
So it could be very, very precise, and it only depends how well you design the system that controls them. Attitude and orbit control system.
No, not satellites, but some planetary configuration that would allow for eccentricity infinitesimally small.
So very often they are actually very small. The Earth around the Sun, eccentricity is very, very small. There's almost no change, say, in distance. A little bit. I think the perigee is in January. January we're a little closer to the, I think it's like January we're a little closer to Earth than in July.
It's the opposite of what you would.
But it's not much. It's pretty close to a circle. The reason for that being that most likely when the solar system evolved, the friction made all these rocks. Solar system consists basically of rocks and dust at the beginning, made them being quite circular, and then planets formed. So it's pretty close. And then if you make a satellite, you could control that. And if you have a mission that requires an extremely circular orbit, then you just need to design, you guys, over the control, you design to do that. It could be done. One of the things you have to take into account is the very odd gravity of the Earth, which is not at all, the Earth is not at all a sphere. So, we have repeated the Keplerian elements. And you know there are a number of orbits. You should have seen it just to check with you. We have this orbit here. Who can see that? Can you see that? And Natalia, can you see that?
Yes.
So, to give you an idea, that's pretty far away. This geostationary orbit. We have an orbit of low Earth orbit, which are very. So the geostationary orbits are usually with zero inclination, right? They're around the equator. Otherwise, they make no sense. Then we have very typical orbit is low Earth orbit, and that's in the CubeSat world the typical orbit. Very close to Earth, very often close to over the poles, near polar orbit. What's the name of the most important workhorse of the Indian space program?
PSLV, Polar Satellite Launch Vehicle.
Polar Satellite Launch Vehicle is because most of these small satellites, they go all to polar in these kind of orbits. And then we have this red one, which is an elliptical orbit. And I turn my attention to our Russian lady, Molniya orbit. They're very important if your country is very northern, like Russia is, and you cannot reach them with the geostationary satellites, then you do something like a Molniya orbit. It has similar features as geostationary orbits for countries that are very close to the poles. So if you need a permanent communication satellite over your head, but you are close to the poles, and geostationary satellites don't work, you choose a Molniya orbit. Or you are in the United States and you want to spy what these countries are doing, then you put your satellites also in these orbits, because then you can see very well onto that country.
Why not just use a lower orbit and tilt the plane of rotation?
Say it again?
Why not just tilt the? I mean, the only parameter is the distance of the satellite from the Earth.
Yes.
So why not just launch it from a different position, shift the direction of the Earth?
I'm not understanding the question.
Imagine that blue line.
Yes?
It's just shifted.
Shifted how? Like this?
Yeah, I mean, there's no real up and down when you look at the Earth from space. So why not just put the satellite in such a position where it passes over different countries? Why does it have to be a polar orbit?
So if the satellite goes in a circle or an ellipse, it needs to go through the center. So the center of the Earth needs to be in the same plane, right? So what you, in theory, could do is you could rotate it, change inclination, which costs you enormous amount of fuel. That's why you launch it into the inclination that you want. You could also change the right ascending node, which costs you an enormous amount of fuel, most likely not even possible. The energy that you require to change It's just enormous. The kinetic energy that you have in this, say, if it's a low Earth orbit satellite, do you know the speed of a low Earth orbit satellite? So you better know it by heart. It's 7.5 kilometers per second. You know the duration of a low Earth orbit satellite? How much? How much does it take? 90, around 90 minutes. It is wrong for Muslims if they have to pray 5 times a day, that they not stop praying. Low Earth orbit takes, it's very fast, and 90 minutes for one. So as far as I think it's not a myth. I think it's true that when they had the first Indonesian astronaut in the International Space Station, which is in low Earth orbit, it actually passed a law that he does not have to pray 5 times a day. Because he's not stopping praying anymore. He's not doing the astronaut's job. So 90 minutes. What is the duration of that geostationary satellite?
24 hours.
That's important. I hope that we know that. So this is just a recap of the different orbits, and what is important for them. Sami?
Just a question. So the red orbit is more like when you want to observe one spot of the planet, and the blue one would be to probably Earth. Can I understand this correctly?
Okay. First of all, you touch an important point that is just here. These satellites have different ground tracks. And indeed, that's going to be one of the important parts that you will have to look into for the payload. When and how can you see which spot on Earth? Yeah? So, if you like, you can come close. We have geostationary satellite, which is constantly here, right? So 24 hours. So it can see roughly this part permanently. The Molniya orbit is very fast at perigee and then very slow here. So it stands a long time over Russia, which then the Russians can use as to communicate or receive TV or whatever, or the Americans spy on the Russians. And it has a ground path like this one. As a matter of fact, why is it like this? Yeah, so it's very fast. The Molniya orbit is very fast here. It would move like this very quickly, and then would stand, for example, a long time. In this case, over Canada. Would stand, move, then go down fast. Would stand over Canada, speed up, and then so ground track. Something that is then very different for the different kind of orbits. In the cubesat world, they remain with low Earth orbit, and they have such a ground path. They fly like this. It looks as if they would change direction, but they don't. It's just when they fly over the poles. Can you see that there? When they fly over the poles, then it looks a little strange on a 2D map. Yeah? But this is how they ground path looks like. It takes 90 minutes from here to here, and there is some particularities which will be on the next slide. So while they're moving on in that orbital plane, the Earth below them rotates, but there's something funny happening then there. Let's see that.
But Molniya orbit, we also have the that effect of the rotation of the Earth, right?
Yes.
So after
Yes.
one day, in this case, Canada would move away.
So I think you can. So yes, and I think typically you have like 3 satellites at the same time in these Molniya orbits. And their duration is somewhere in between. I don't know by now, 8 hours or 12 hours or this order of magnitude. Then they have like 3 that you always have one of these satellites in view. I don't know the details. Education outcome for you is just a recap of the different orbits. This is what typically the other people like Simos and so have in mind, because the research all focuses on SES and so. while in the low Earth orbit, the CubeSat world, we go to low Earth orbit. Your satellite should go to low Earth orbit, to one of those near polar orbits. So the environment in low Earth orbit is not perfect. There are perturbations to it. So the satellite will not follow perfectly circular orbits. Just to give you an idea, what are the important perturbations? This is the altitude from 0, 500,000, 1,500, 2,000. Roughly, this is called low Earth orbit until 2,000 kilometers altitude. So way below geothermal satellites. And then you have a normalized perturbation force on the y-axis. And most intuitive is the drag. That's the atmosphere. That is obviously high, very dense, close to Earth. It's very, very thin, higher. The forces that are caused by drag go down with altitude. So far, that's quite clear. There's the moon and the sun. There's our sun. If this is, say, the Earth, and the Earth rotates like this, and together with it, maybe satellites, the sun will have certain gravitational perturbation to it. Relatively constant over the altitude range, of course. And then there is this funny thing is called J2. That will be explained on the next, on the 2 slides later. That is a gravitational effect of the Earth itself that impacts your orbit. And that's actually going to be quite important. It goes slightly down, but not much. So in low Earth orbit, your satellite that will be from here to here. Yeah. Whether you will be in 500 or 1,000, the drag will change quite a bit. All the other perturbations will not change much. You don't need to compute that. The J2 effect, I will explain that it actually, certain things are quite simplified because it exists. The drag, after all, is pretty small. If we do not have extreme requirements on circular orbits, it's not going to impact you much.
What are the other J's? J3, J4, J5, they are also.
On the 2 slides further. These are the little brothers of J2. That's why they're called also J. That fun is also fine. SRP, solar radiation pressure. It's very little, but the photons that impact your satellite, they push it a little bit. Tiny.
So solar cells, but it's the same principle with which the solar cells.
So people build spacecraft that have solar sails to possibly fly to an asteroid with it. Advantage being,
You don't need fuel.
you don't need fuel. You have a big solar sail, but you don't need fuel. Quite right. And it's very tiny force. However, at 500 kilometers, it's already bigger than the drag. And if you have time, well, you can use it. And if you have long-term missions, say you fly to an asteroid, you better take that to account. Because over 10 years, that accumulates to quite a force. So your trajectory will change, will move somewhere else if you neglect that pressure.
Why is this RP, lunar gravity, and solar, or why are they constant? Why would they be constant?
They're constant over the altitude because
In proximity to the moon, to the sun.
this is the sun, this is the Earth. The gravitational effect of the sun goes down with the distance to the sun, which is, I think, 150 million kilometers. It's the distance of the Earth to the sun, 150 million kilometers. So the difference between from here to here
It's negligible.
is negligible. That's why it's constant. The same is for the solar radiation pressure. It depends on the distance on the sun, and therefore over this range, it just constant. If you fly to an asteroid, the solar radiation pressure changes a lot if you go further away from the sun, or if you go like There's an American probe now, the Parker probe, that goes close to the sun. As a matter of fact, extremely close. Like this, solar radiation pressure becomes big. Important for you to know, this is the environment is not constant there. And the J2, we will use it. It will, as a matter of fact, it will make certain things easier for us. We'll see that. Yeah? A word on the drag. This is again altitude from 0 to 1,200 in this case, and the density, it's here in relative terms, goes down exponentially. E to the power of minus 15 kilogram, that should be per cubic meter down. So it's obviously very high. If you were to fly a satellite, 0 altitude would experience a lot of drag. If you higher you go, it's less. And I guess hard to see, but here, for example, we have a model of a spacecraft which is solar sail, which they use in this case as a drag sail. I was involved with these guys, so yeah, it's hard to see, but you can, if you build a big sail, you use it either with solar pressure or you also catch the drag. What happens then is you deorbit quickly.
So like paragliding?
Yeah. Or you just create drag. And that's what people also do. They use big sails to deorbit their satellite. It's kind of illustrated here, but it's not very clear. This is the one perturbation, the drag, that has some impact on us, and the other one is, is the solar radiation pressure. Before we come, the other one is the J2. Before we come to that, have you heard of the solar cycle? Solar cycle.
With the release of the solar flares, is it that?
Yeah, Michelle, ever heard of solar cycle? No.
Like coronal mass ejections?
Yeah.
Solar
Solar activity.
Solar activity.
Yeah. So it's sometimes this 11-year cycle is sometimes mentioned. Many people, few people know what exactly happens, and I don't either. But many people know that there's an 11-year cycle where the sun becomes very active or slows down.
Okay.
And it's interesting because this is actually known for centuries, because it depends on how many sunspots there are. And already centuries ago, people were looking at the sun and counting the sunspots. And by this, that's why we know very well for centuries that there's this 11-year cycle. It has an impact on the drag that I showed on the last slide. Because when the sun is very active, we receive more radiation from it. Some people say it affects our electronics. I'm not convinced of it. But what it definitely affects is it heats up the atmosphere. And then the drag is higher. That impacts our cubesat flight. Because we fly low Earth orbit where we still have drag and the solar activity is high, then we have more drag.
So does the solar maximum and solar minimum affect the solar radiation pressure or the drag?
It affects, that's a very good point. It does not impact the solar radiation pressure. That seems contradictory. That needs further explanation. First of all, it affects the heating of the atmosphere, and then the atmosphere increases in size because it's hotter. And if the atmosphere is bigger, then we have more drag. The solar cycle has to do with the activity of the sun, and that's particularly changing in the UV, ultraviolet. And that's heating the atmosphere. And the general radiation or light from the sun is not changing much. That's why we don't see it. It's not that we get more sunburns when the solar activity is higher. The general light is quite constant, but in the ultraviolet, there's more heating. So more radiation, and that heats up the atmosphere. And so we are now 2019, we are at the end of solar cycle 24. So this is 22, 23, 24. You see that the maximum of these cycles have been much higher in 1990. The maximum go down, and at the moment we are at the bottom of solar cycle 24.
How it was calculated? Why it's just 24th cycle?
At some point, somebody started to count.
Should be the age of the sun divided by 11.
Yeah. I guess this is so 22 times 11, so it's 230 years old, and it's what you see here is the number of sunspots. 200. This is what people really count or century ago. Just look at the sun and count, and by this you can see solar activity. It's one of the few, say, information related to space that is available for centuries because it was so easy to measure.
And it really goes close to zero. And
But the sunspot numbers doesn't mean that the radiation goes to zero.
yeah.
But
Just
in,
sunspots.
if the sun has a quiet time as it is now, we may not have any sort of sunspot. And there's websites, you can just check how many sunspots do they have today. Likely it's around zero nowadays. Anyway, it changes the radiation, the heating of the sun, the earth, and so that the drag.
Is it also related to when the magnetic field of the sun is created by the head?
Quite right. So the magnetic field changes direction every 11 years. It's a bit, it was explained to me that the magnetic field goes like in the Earth from North Pole to South Pole, and due to the rotation of the sun, it's like these magnetic lines, they wind up like spaghettis, and then they turn around, and then you have a new cycle. You need to go ahead. Our friend J2. So we have the Earth here, only half of it, which is displayed here as circular, however it is not. J1 is just the potential, the gravity potential, first order of a series shown here, where we sum up certain J's together with the radius of the Earth and the distance from the Earth. For you to keep in mind, there's a series that defines the Earth potential, and if you make the series only sum it up over 1, we have a circular Earth. But that's not enough. If we sum up over the second part of the potential, we'll have to take into account the flatness of the Earth. The Earth is not a perfect sphere, it's more flatter. That's because it rotates, so it has forces that makes it flat, a bit like a pancake. That's shown here. It's symmetric with respect to the equator, but it's flat. And if you sum further, then you have a bulge to the bottom. It's J3 that was shown as a perturbation on one of the last slides. And we have the bulge to the north pole or to the north side. It's called J4. They're not equal. Gravity potential of the Earth is not perfectly spherical. It's perturbed because it rotates. It's not perfect. Earth is just not perfect.
So they're like corners.
It's a potato. The Earth is a potato. And since the gravity depends on the mass distribution, in space you do not have all the time the same gravitational attraction.
So they're the densest spots.
Yeah, that's either the amount of mass or the shape could be different, or it's more dense here than there. There's different things that come to account. This I actually don't know. For me, my mathematical model is important to know. It's not perfectly spherical, but the potential is different.
So J1 is perfect sphere, J2 is square sphere, and then J3 and 4 is potato.
It bulges to the south and to the north, yes. And you could continue this. And of course, this is all symmetric around the axis of the Earth. Also, if you go around the Earth like this, it's not perfect. The Himalaya may have a bigger gravitational potential than, say, the other side, the Americas. That goes way too far. It's not relevant for us. For you, not perfect. This the reason you know because it's not a perfect sphere. On the equator, the radius of the Earth is 6,378. Over the poles, it's much less, 6,356. In our world, we typically use the average of it, which is 6,371. So it's quite in kilometers, quite a difference there. So I'm way too slow. So why do I talk about J2? No. Let's rest the J2 for a second.
Just a question on the last slide. So when you showed the different spherical, so how does this change? Like, how do we know? Is it time dependent or is it?
No. Well, this is just the Earth is potato shaped and not a sphere.
You have like 4 different angles that you show. So
No, this is not really angles. You sum it up. This is a series. If you sum this plus this plus this plus this, you end up in a more realistic shape of the Earth, a potato shape. You sum it up. That's why you have a series here. However, those are not important. J2, however, is important. So the flatness, the pancake shape, that is important. Next slide. Yeah. Important for you to know it's flat. It has impacts on the orbit, and there is different equator. Let's say different radiuses. It's high at the equator, low at the poles, and then there's an average to find. Next slide. Is first of all, it's about typical cubesat orbit, and a typical one could be the International Space Station orbit that has an inclination of. Natalia, why is it 52? It's 52 inclination. Do you know why? Because they wanted to launch also from Baikonur. Right? Because it's international, you launch from the United States and from Baikonur, and so it had to be 52 degrees. So it's a typical orbit. An orbit possibly we will be launching in, so we could possibly bring our CubeSat to the International Space Station and launch it from there, and then it will have the ISS orbit.
So basically the ISS always sees the sun.
No, that's wrong. So so this is inclination is 0. If this is our this is ISS a circular orbit, but forgive me, it's an elliptical orbit. 0 would be approximately like this. 52 degrees would be approximately like this. And now I want you to understand what the beta angle is. So there's the Earth here. The Earth, blue, and the orbit of the International Space Station inclined 50 degrees. It could be that the orbital plane is like this. Then, those you have to imagine, at some point the International Space Station is behind the Earth. Right? So it's in shadow. And so the angle between the orbital plane and the Sun is 0. Now if I move from spring to summer, now the angle, it's now 90 degrees over the plane to the Sun. And now the International Space Station is most of the time in sunlight. Is that clear?
Can you repeat it once again?
So it's unfortunately my Earth is flat now, but you can imagine it's a sphere or almost a sphere. And this is now with the ISS orbit is like this.
Yeah.
So you have the sun, a sun ray towards the Earth. So this angle, say this ray, the angle between that ray and the orbital plane, and now it's 0.
0 degrees.
So whenever I set the ISS is here, it's in shadow.
Yes.
I'm here. Now this angle, the sun ray and the orbital plane, is 90 degrees. Now the ISS is either never or rarely in shadow. So if you imagine that to be a sphere, now if the ISS is, say, here, it's still in shadow, but only for a very short time.
Yes.
Yes.
Yeah? The beta angle tells you how much sunlight you receive. Why is that important? Power engineering. Why is sunlight important?
For our solar panels?
Yeah, so if you have a small beta angle, you produce less power. If you are in an ISS orbit. So another thing is heating. If you are, say, here and you receive a lot of power, a lot of sunlight, you produce a lot of power, but also you receive a lot of heat. So in the International Space Station or with Apollo mission, you often have the problem to cool down. The beta angle is important. With the beta angle of the International Space Station, and it does like this. It has a, so it's not well visible, but it does. This is 1 year. It's like a sine wave, goes up and down. We go once around the sun. I go okay. But it does the second thing. The second sine does like this. And this is because the orbit of the ISS precesses. It does like this.
Yes.
So it does like this. Who's the culprit for that? Who's responsible for that precession? It's the J2. The J2 perturbation that you saw 2 slides before. Because the Earth is a pancake, it makes the orbit precessing. And I mentioned that the J2, while it makes the beta angle very complicated, we can use it to our advantage.
It makes the orbit what?
Precessing is this movement. And depends the inclination. If the inclination would be 0, there would be no precession, it wouldn't make a difference. If the inclination is 90 degrees, it wouldn't make any difference either. But if it's in between, for example, 98 degrees, this precession is very slow. And then there is a value. I'll put the equation here, but forget about it, because the equation. The precession, there's a value when this precession takes exactly 1 year. Until now I've shown you orbits where the right ascension of ascending node stays constant. Right? Is this the ellipse like it is? This part how the ellipse is in space. Until now I've shown you orbits like this. Now if you add a precession to it, then the orbit, and the precession is very slow, then the beta angle stays constant. I'll demonstrate it again. In principle, an orbit, the orbital plane stays fixed in space. It does like this. Beta angle high, beta angle low, beta angle high, beta angle low. Stays fixed in the plane. Unless you add precession caused by our friend the J2, the pancake. So it changes now. And so it would move like this. The plane. The plane of the orbit always points with the same angle to the sun.
Is this an extreme case?
No, that's actually very, very common. Or it has certain properties that are so useful that, in particular for CubeSats and any kind of low Earth orbit satellites, is so useful, so exploitable, that if we launch our CubeSat, it's most likely going to an orbit with that property.
That will be faster.
And what is this advantage? This on the slides? We'll talk about it.
So the ISS doesn't have this effect?
No.
Because it's too big?
No, because it is in 52 degrees inclination. In order that the precession has exactly 1 year, it would need to be in a higher inclination. Now, why didn't they launch the ISS into a higher inclination? Because it needs a lot of energy.
Yeah.
If you launch into the depth, so now it's the Earth, say the Earth rotates in this direction, and you launch into that direction, you save a little bit of energy, because you use the momentum from the surface of the Earth. It's half a kilometer per second, so it's a lot. You need to go to 7.5, sorry, half a kilometer per second, so your rocket can be smaller or cheaper. Now, if you increase the inclination, so you go north, you don't use that speed anymore. Your rockets need to be bigger.
Yeah.
So they wanted to have, if you can, you want to have as small as possible inclination. For example, 0. Now, since the Russians were involved and they want to launch from Baikonur, then they say, if we want to reach from Baikonur to ISS, we need to have at least 52.
Yeah.
But then that was also defined as the maximum. If they they could have gone to that orbit, the sun-synchronous orbit, but then they would have bigger rockets or smaller payloads or more money.
So the advantage of having this orbit were not big enough to specify why they would launch.
For the International Space Station,
Yeah.
correct. Now there are other missions for which this purpose, the precession equals 1 year, is so useful that they always do it. And that's why even the Indian rocket is permanently launching into the polar orbits, and they even named the rocket after that. Because say most of the launches that go to low Earth orbit go in this kind of orbits that have this property. We'll look into it, why is that useful. We will also go there, not because we need it, but because there's so many launch opportunities. So our CubeSat is secondary payload, so we go where we have a launch opportunity, where the bus goes.
And the period of one full rotation is depending on the angle.
Yes.
Okay.
So typically, it depends. The formula is here. I is the inclination, the rest is all the constants. This is the precession rate, so we want to have that to be 1 year. So then that defines the inclination. It's typically 97 degrees. So it's it's almost polar. And we are already. So we need to. So we need to stop here, otherwise taking too much. In essence, it's illustrated here. It's called sun-synchronous orbits. The red is the one without accounting for the precession, so it stays constant. If you take into account the precession, then the orbit rotates over the year, precesses.
So for that, we have to maintain inclination higher than 45 or something.
So yeah, it's defined by that formula, and it's for low Earth orbit altitudes between 98, 97.
19.
Yes. So the Earth, the equator, the inclination is that angle. 0 at the equator, 90 if you are over the poles, and these sun-synchronous orbits is typically around 97, 98 degrees, this order of magnitude. So it's a little further over the poles. And then the precession is exactly 1 year, depending on the altitude. And then you have this special property that we're not having time to talk about it today, unless you give me 5 more minutes. You want to know?
Yeah.
So you are the sun. This is the Earth. I mentioned that if the camera is the sun, now you always point with the same side of the orbital plane to the sun. If you are the sun, what time is it here at that point? Exactly, it's exactly noon. So you could have, for example, a satellite, very typical, that crosses the equator at say 10:30. So we have this kind of orbit. Satellite crosses at 10:30. This is a very, very typical orbit. Almost like our satellite will go that, and it will cross always at 10. And because the precession is exactly 1 year, no matter if it's autumn or spring, the satellite will always cross over that spot when at that spot is 10:30. So imagine you have the Eiffel Tower here. The sun is here, so it throws a shadow in this direction. The shadow, you can see it. So that's the Eiffel Tower, and that is visible now. Satellite moves like this, so it's around 10. It sees always that spot on Earth at 10. Yeah. It means the lighting conditions are always the same at that spot. So if you have an Earth observation satellite that uses visual light, it's perfect for a camera because that spot has always the same lighting, and the shadows have a very specific length. So if you want to observe the Earth with visible light, for whatever purpose, be it agriculture or because you are a spy satellite, and watch what the Iranians are doing on their launch site, then these orbits are perfect. Because you don't need to know, you need to change the optics of the camera. And because you know how late it is, and by the size of the shadow, you know how big the object is. You know how big the rocket on the launch site is because you can see it on the shadow.
Yeah.
So for any kind of optical Earth observation, be it civil or be it military, these are perfect orbits. And they could also launch in this. Then this would be not a 10:30, but it would be a noon orbit. Could also do this. Then at this point there is more light, because you are just in the view of the light, but you see no shadows. If you go a little further left and you have an orbit that crosses at say 6:30, then you have better shadow, but you have very little light because it's already on the edges.
Yeah.
So therefore this 10:30 is a good orbit. The satellite always crosses the equator at 10:30 or a little earlier over Paris. The lighting is always perfect and good for your optical observation. It's not so good here because less light, not so good here, it's more light but no shadows. Now the American spy satellite is called Keyhole. Keyhole is the one that when Trump twittered this photo of the Iranian launch site, it was a Keyhole satellite. There's 2 of them, say 3 or 4. 2 of them are in 10:30 and the other one are then a little later at 14:30, around order of magnitude. Now the shadows in the other direction.
Yeah.
So if you have that, you have perfect visual observation capabilities, and if you on a spy satellite, then you may want to have 2 or maybe 3 or so to observe in the morning and in the afternoon, which also means if you're a terrorist, do something critical, not at 10:30, 14:30. If you're a equator, do it at noon or say at dusk or dawn. Then you know the kilo satellites are not there. But this is for military purpose very good orbits because of the shadow, because of the sunlight. There's a very special orbit in addition. It's the 6 a.m. that crosses always around here. Or if we look from here, the sun comes from here. So this is in light. And this is in dark. So if you are the sun, then this orbit is 6 a.m. this orbit. Or if your sun comes from there, you look from here, and your satellite flies from here to here. You always look at, it's called the terminator, or the line between day and night. It's not good for visual optics, not good for looking, because it's always a little dark. But this orbit has another advantage. Satellite goes from here to here. It always sees the sun. The sun is never in eclipse.
It's over in the sun.
It's always in the sun. So power people, what's good to be always in the sun? Produce power. So if you have a satellite that you still want to be in low Earth orbit, but you do not depend on lighting on the ground because you have a GPS occultation or a GPS reflectometry mission. You don't care about. You don't care about the sun on the ground. You may want to choose an orbit that is 6 a.m., 6 p.m. Is this? Now our orbital plane is perpendicular, so it's say the vector. Say this angle is 90 degrees to the sunlight. If you always do like this, our satellite is always in the sun. And we don't care what the sunlight on ground is, because reflectometry does not depend on it. But we would care a lot about always sunlight, because then we produce a lot of power.
Yes.
So for our mission, say if I'm making your homework already, this orbit would be the best from a technical point of view, but there are not so many launches to go there, because it's not so useful for other people. So most likely we will not have it, because we will not find a bus bringing us there. But technically speaking, that would be the optimal. With this I close. I had more. Like many other lectures, I thought I'm much faster, but we'll repeat all this then in the system engineering section lecture in 2 weeks. For next week, I gave you a little homework. You've seen it on Moodle. I gave you a number of papers. I want each of you to choose a paper and look for the particular aspect of your discipline. You may choose a paper and read what they do for attitude control, and I want you to put this on, say, 2 PowerPoints, like what you found in that paper on attitude control.
A short presentation.
1 to 2 slides, just the findings. If you choose UFTI satellite, do this. Yes. 1 paper, 1 aspect. For example, if you find an UFTI paper, there's a 1-unit CubeSat there. They have a very primitive attitude control, only consisting of magnetometers and magnetorquers. Primitive. I want you to know that. You choose one of those papers and look into how much do they address power generation storage there. Just in 1 or 2 PowerPoints, summarize your findings.
Is it a group assignment?
No, it's each person should find 1 paper and summarize that aspect for the discipline. And if you don't like the papers that I put on Moodle and you find another one, that's fine. For me, it needs to be somewhat relevant. So don't come with the International Space Station. Try to find something that has to do with, say, cubesats, or reflectometry, or something. Yeah? Learning outcome for you is to get a bit familiar with cubesats, your discipline, reflectometry maybe, and so on. Sorry that I also much overtook my time, and I hope that at least the LEO astronomy was kind of informative. Yeah. So I will not be here next week. There's Sajjad Tabibi will give a presentation next week on reflectometry. He's the specialist. And then you should start to summarize your findings of the literature review. 3 groups should present next week. The others are listening. The week after, the other 3 groups shall present their findings.
Next week already?
Next week.
So next week I'm not here, but another person, Sajjad Tabibi, will be giving you a lecture on reflectometry.
So we're supposed to present at that lecture?
He will presenting it.
So you only see half the presentations? Will they be recorded, or how will you grade them?
Should we present our
Next
assignment?
week, will we have presentation?
You will have presentation for your assignment. You go to Moodle, you find one of the papers that you like. Since you're the payload person, you look for maybe one of the papers that addresses reflectometry and just address in few words what you found. There's no grading. The purpose for here is only that I guide you, that you get familiar with your discipline and cubesat engineering. I'm not grading you.
So I check the paper and then I prepare a small presentation.
Yes.
With PowerPoint, without?
For example, PowerPoint.
How long? 5 minutes?
So you will not have more than half an hour. 3 groups presenting. It cannot be more than 5 minutes.
So in our case, we will present chapter 11.1.
So
Just checking, so we have 1 hour class.
Oh, yeah.
We have a class of 1 hour from 3 to 4.
Correct. I'm sorry that I overtook.
No. We are asking about the next class. Should we have a lecture and presentations in the same class?
Yes. So the lecture should be not more than half an hour.
Okay.
And then there will be 6 short presentations of you.
Then for presentation, it will be at least 10 minutes.
No, 5 per person. So next week, 30 minutes presentation of Sajjad.
Yes.
Then there's 30 minutes left, which will be divided among 3 disciplines. It will be payload, power, and I forgot who the 3rd group is. But each group has 2 people. So there will be in total 6 mini presentations. It's not even a presentation. Yeah. If you on one PowerPoint slide just say, this is the mission called UFTI. We'll find a paper called UFTI. It's a 1-unit CubeSat. They built it in Liège and launched it. It worked 2 days and then it broke down. It's part of the game. So you may find that. So imagine you're in charge of attitude control. You take that paper. You see how did they do attitude control in UFTI. I put on one slide. It's magnetometers, magnetorquers. This is how it looks like. They do not achieve, so now I'm doing it so that you cannot choose UFTI anymore. They do not achieve a precise attitude control. They only achieve an attitude stabilization. With these magnetometers and magnetorquers, you cannot really point, but you can avoid that the satellite is wildly rotating.
So it's important that same people in the same group do not choose the same paper, right?
No, everyone could do this a different
No, but
paper.
if the same group people choose the same paper,
Yeah.
they will be repeating the presentation, right?
Yeah, maybe you can coordinate.
Yeah.
So-
I'm just asking.
Only 3 disciplines next week. The other 3 disciplines will be the week after, so they are lucky, they have 2 weeks. 3 disciplines, each consisting of 2 people. Each of them shall summarize their aspect. As I said, if you were to choose UFTI, you'll find out magnetometers, magnetorquers, no good attitude control. This is a picture maybe of it, of the attitude control system. And that's about it. Learning outcome for you is there is a simplistic way to control attitude control, to control attitude. That's all. I want you to learn it, and I want you to understand there is this way. Yeah?
So each of us should have presentation, or as a group we
So,
can choose?
not each person is individual. Next week, 3 disciplines. I don't know, now I don't know by heart. No, I don't have it here, but it's on the Moodle. 3 disciplines next week, each discipline consists of 2 people. So it will be in total 6 presentations. Presentation, I mean 1 PowerPoint slide. Let me reduce it. 1 PowerPoint slide, just what you found. If you choose one of the, say, if you choose UFTI, you will be able to say it's 1 unit CubeSat, so the surface is very limited. You should find out that with 1 surface, you can generate 2 watt of power, unless it's in low Earth orbit, because then you are half the time you are in eclipse, in shadow. So it's only half, it's only approximately 1 watt power generation that UFTI can produce. This is the learning outcome, that you understand there exists UFTI, 1 unit CubeSat. The order of magnitude of power generation is 1 watt, orbit average. I don't want you to do more. Yeah?
But everyone will talk for 5 minutes, or we combine us with 5
Principally,
minutes.
you can work together, but I want each of you looking at another publication. Yeah? Do not do too much, and I know publications are difficult if you're not in the field. Just condense a bit the information. But we need to get started somehow, because in the end, we want to design a mission. But saying I also have a homework, and I'm doing it. My homework is to get the money to launch it. Yeah? And you have to help me with that. You need to make a good design. For that, you need to get going. You need to understand the things. Okay? And 2 light elements will be fun for in 2 weeks. Sorry again that I took much more time.
So the assignment is so we can do that.
It's written on Moodle, yes, what you have to do. Yeah. Michelle, everything clear? Right?
My eyes are already on the same spots.
Otherwise, you okay?
Yeah.
Okay.
So will they be taped presentations for you to see later, or?
Yes. First of all, this is for you to read a bit about CubeSat's reflectometry. That's why it's not grading there. And you may send them to me, yes? Oh, we don't need to record it. But you can send me the PowerPoint. Yeah?
8 minutes to next song.
I think I don't understand. Is that we are both going to do presentation in 5
The slide.
This is actually better.
So,
It's probably the equals.
next week you will meet for 1 hour. Today it took much longer. I'm sorry, it took 1.5 hours. So next week we'll meet 1 hour. For half an hour there will be a presentation of a lecturer. Who is the expert in reflectometry? Reflectometry is the measurement method that we will use. Remember from last week? We will use a method called reflectometry to measure the moisture, the water underneath. So he will present you that method. And then you still have half an hour left. And I want and I want
for pleasure, or it's
so that will be
next try.
They take strong coffee, but strong tea. There's no problem.
let me see.
Normal. No, it's not normal.
It's an active desperation of
I always
So next in total 6. It's not really presentation, okay? One second. Fine. Yes. Just for you to browse through to get an idea what.
वही खींच ले बोला खींच ले फायदा है
मेरा तो पता ही नहीं ना इसमें
कि उसमें नहीं लिखा ऐसे ही ना
नहीं लिखा ऐसे लिखा नहीं होता ऐसे ऐसा ही होता
सब क्या है तो जादू What time is the class next class, huh?
Now it's in the 5 minutes.
So you like to
Okay.
Maybe I meant
I'm sending emails and
not there. I think it should be there, but
Where is that? Really, talk with. You talk with
that is no problem. We won't make mistakes. If you have questions, also let me know. I think it's a little bit more difficult for you than for the others. I know. Okay, so but then just come to my office. We can discuss the things. Power engineering is not simple, not at all. Yeah? No. It's not easy. Okay, so but you have you're a member of your group. She's electronics school. She knows a bit. I know, but you come to my office to discuss it. Yeah? So at the moment I'm not traveling much, except next week. So most of the time I'm coming with the same train as you come, and I'm there until 6:30. But next week I'm traveling. That's why I'm not here. So you can just come to my office. Now the problem is the door is closed. So you need to you need to call me. I need to let you in. Yes, you send me an email that you want to come, and then you need to write down my telephone number. Call me, and I can open you the door.
Yes. What is the expectation from the systems engineering